time. And in fact, you don't even have these slides, I realized as well. But I'll give them to you. Okay, so we're going to talk about mixture models, and I went through this briefly last time, and we're going to try to have a little bit of a slower lecture today, hopefully a little bit easier pace. Also, by the way, I think we're going a little bit faster than normal, so do feel free to stop and ask me any questions you may have, okay? Because I think otherwise we're going to finish the course early in some sense, but we can do more material, but it's better to, I think, try to understand the material that we've already done better, rather than just doing more material. Okay, so mixture models. These are a form of latent variable model, and this is all to do with the hidden variable stuff that we've been talking about recently. So how to train models with hidden or latent variables. And I tried to sort of point out that mixture models are the kind of latent variable model which is often used for clustering, not always, but it can be used for clustering. So the idea is that we're going to have a, say, in general, maybe some kind of bunch of data points. Okay, so they might be clustered somehow. So in this probabilistic modeling framework, the idea is that you're going to make a generative model of the data, right? It's all about making probability distributions. And so here you might say, well, look, you know, there's 3 clusters apparently. So what we could do is we could say to generate data from this space, you could say first choose a cluster, 1 of the 3 with some probability. So for example, we might choose this one here. And then given that cluster, you might then generate data from a distribution associated to that cluster. So for example, you might generate data from, say, a Gaussian distribution, which has got a mean here and some covariance around that. Okay. So what does that mean? Well, the generated model would then say, well, okay, you generate something from H, could be an index from 1 to 3. So it generates a cluster, H, index. And then we generate some data V given H. And that will be our model. Okay, so we first of all generate a cluster H, in this case 1 to 3. And then given H, we generate a vector for the actual data point here. So actually this Gaussian actually could in principle generate a data point out here as well, but it's just extremely unlikely. So the idea is then, given this, you know, this is a model which you could parameterize in some sense, say by theta. So you're going to have general parameters for, say, this point, here, and this one on there as well. So we're going to try to then, say, learn the parameters. You know, so given that you're in cluster number 3, what, say, is a distribution which is appropriate for cluster number 3? So it might be Gaussian with a mean here. So the mean would be dependent upon the cluster index. And similarly, the covariance might depend upon the cluster index as well. Or you might have a sort of, if there's a lot of data, say, associated with this cluster, and only a few data points associated with this cluster, what would you expect? Well, we'd expect that the probability that we generate data from cluster 3 is much higher than the probability we generate data from this cluster. Because there's more, it's just more likely that, you know, we want to generate data from cluster 3 because there's more data in cluster 3. Okay, so another kind of thing I want to observe is that in these sort of discrete mixture models where this H here could be, you know, just an index from, you know, the integer set, it doesn't matter if we call this cluster number 3 and this cluster number 1, or this cluster number 1, this cluster number 3. It's just a kind of indexing, right? It's really, we can just reorder or permute these indices at will, and we have the same model. So what does that mean? Well, it means a little bit that there's a kind of, there's always going to be a symmetry issue in this parameter space. You know, why do I, if I want to learn the parameters, you know, and then I've got some kind of, I've got some identifiability issues, you know, should I really, first of all, the parameters need to say, well, I'll call this one parameter 3, and this might be parameters 2, this might be parameters 1. But how does that identification happen in a model that's formally agnostic to this symmetrization issue? Right? So what will happen typically is that numerically you'll get a breaking of the symmetry. There's no, the model itself is formally fully symmetric. There's no, it doesn't know that this is cluster number 1. It would just assign the data at some point. Say, okay, I'll call this cluster number 1. And that's just to do with, maybe some kind of quirks of your operating system or your, the way that you do the calculations on the computer. So this is called, this issue is called identifiability sometimes. It's not possible always to sort of uniquely identify objects to models. Okay, so let's just go through this. Okay, so yeah, in this mixture models, for the discrete case, we have a discrete H. Okay. We can also talk about continuous mixture models, which we are not going to do, I think, in this module, but that would then involve obviously an integral over H. And yeah, I'm going to call this B visible, and the H is going to be hidden, or some kind of index. So yeah, for us who do probabilistic modeling, it's natural to think of at least one class of clustering to be basically related to these discrete mixture models. So this is our, a simple graphical model for this. So we've got a hidden variable for each data point. So that's a cluster that it belongs to. We've got a sort of distribution, the output given each cluster, and then we just replicate that over the data points. So if you assume the usual IID property, the independence property of the data, we can sort of replicate this. And then we're going to have some parameters for the prior cluster index and some parameters for the generative model data. Now, so I want to look at a specific model now. This is one that you can use to do customer clustering. So we're going to use this in a minute to do clustering of supermarket data. Okay, so we're going to try to take a whole bunch of data from, say, let's say you have, a customer. Okay, so you've got, say, 10,000 products in the supermarket, and this customer buys various products. Okay, this is one interaction you had with the customer. And this customer might buy these products, maybe over some time period. And then what you'd like to do is maybe to sort of say, well, we've got certain kinds of customers here. You might have, if you're Tesco, you might have 10 million customers or something like that in your database. And you want to try to understand what kind of customers you have. So maybe you have, people who are, middle class or something like that, and they tend to buy various, Tesco's finest products or something like that. You might have students who are, going for the more bargain basement kind of Tesco's cheapest products. So it's kind of interesting to see, what kinds of people you might have. Right? So one way to do that is to use a simple mixture of independent Bernoulli distribution. So what do I mean by that? Okay, so this V is going to be now, D is going to be going to say 10,000, that might be our number of products in the catalog, and N is going to be our customer index. Okay, so I'm going to call this V is going to be a binary vector for the nth customer. Okay. So in the probability distribution, generating a product vector for a customer is going to be, first of all, we're going to choose a group for this customer, a cluster index. Okay, so from capital H clusters. So we'll assume, we might assume there are going to be 10 clusters. Okay. So we'll generate a cluster. Then, given that cluster, we'll generate a product. Is this person going to buy this product with some probability P of I given H? Okay, so that's going to be just some Bernoulli index. Bernoulli distribution. Okay, it's going to have a theta I H for that probability. Okay, Okay, and that's going to happen independently for each product. So that's where this product over the products is coming from. Okay, and then that's our mixture distribution. So the parameters then are going to be P of H. We're going to have, say, 10 non-negative numbers which have to sum up to 1. And we're going to have then a collection of D times H parameters for this three distribution. We need to learn them. And how can we do that? Well, we could just maximize the likelihood. Or we could use EM to help us maximize the likelihood. So we're going to use EM just for fun. So how do we use EM? So remember, EM got this is two-stage process where we've got, what is it? We've got this expected completed log likelihood, or the energy as I call it. Right? So for EM, we've got this term, the average of the log probability of the joint distribution of visible variables and hidden variables given the data and parameters, multiplied by P of V averaged over the distribution of the hidden variables given the visible variables and your all parameters. And this thing you can call, say, E of theta. This is your energy term. And your task at the M step is to maximize this function with respect to whatever parameters you've got. That's the M. And then the M step will be that we will just essentially, in the EM algorithm, just means computing with respect to this distribution. So what is this in this model? Well, that's simple. It's easy. It's just a product over the data points. So it's a product of dimensions. Multiply vi get theta h. This is this term. So we're going to take the log of that. So we take the log of the products. We're going to get sums and logs. So we're going to get, we'll do this here. So I already P old. I mean the same as P of H given the old parameters. Okay. So just taking the whole thing out, we get this. It's good to get very familiar with this. Again, it's been exam questions actually in the past. Okay, so then we want to basically maximize this thing with respect to the parameters. So how do we do that? So one, we could appeal to those general results that we wrote down last time, or we could maybe for fun just attempt to do it now in different ways. So let's look at an easy-ish term. Let's look at this term here. So let's imagine that somebody says that we want to maximize this expression with respect to P of H. Okay, so P of H only appears here. It doesn't occur in this term here. So we can just concentrate on maximizing this part of the energy alone. So this is a bit where we're gonna do something interactive. So you're gonna help me to figure out how we're gonna optimize that expression with respect to P of H. So the constraints are that P of H, whatever it is, it's just some parameter with a constraint that the sum of the H index of P of H is equal to 1 and each P of H is non-negative. Your task is then to maximize with respect to this P of H. I mean the distribution P of H. You know what I mean, right? Hopefully. Sum over n of the log P of H. P, say, old. maximize this expression with respect to P of H. One way to do it is to use the KL divergence. This is what we were doing before. We introduced this kind of, constant terms, and then we kind of recognize the KL divergences here and there. And then, we could do it that way. In fact, we did that last time, generality. So actually, this is just a special case of that expression. Another way to do it, maybe you're more familiar with this. Is to use Lagrange multipliers. We could do that. Because we've got some kind of constraints. And we'll fudge it a little bit, but it will turn out to be okay. So how would we set up this Lagrangian stuff here?
It's that sum. So again, you end up differentiating with respect to pH.
Yeah.
That sum plus lambda of sum of the pH minus 1.
Yeah. So let's say, I think it doesn't really matter which way we do it. Let's do 1 minus pH. So we could call that the Lagrangian P. So what we're going to fudge is that I'm going to ignore this constraint, as is typically done in the textbooks. It will turn out to be actually automatically satisfied. So, fortunately. Okay, so Conrad's given us a good start. So what do we do next? So this is the Lagrangian. So we don't like this Lagrangian stuff. You need to do the KL stuff that we did last time. So this is a bit more sophisticated, this kind of, Lagrangians, because you have to know about calculus and constraint optimization. It's a bit subtle, all of this stuff. But anyway, this is a classical way to do it. So what do we do now? We've got a function, which is now unconstrained. It's Lagrangian, and we want to maximize this. Optimize this.
Differentiate with respect to B.
Yes, we could do that. So let's differentiate with respect to P. Let's choose a particular component. So let's say pH. So that would be equal to the sum over n. So this expectation is just it's like a linear operator which won't affect it's not a function of let me write it down more carefully actually, so maybe you'll see. So the sum over h of p whole h given bn times by log pH. Okay, and we want to differentiate this with respect to pH. Plus lambda 1 minus pH. pH, and we want to differentiate this again with respect to pH. Okay, so this is a sum over n, so that's not going to cause us any difficulty. We can just bring this derivative aside. this is maybe a little bit, poor notation here. And so, what's going on with this one? It means for every value of h, I've got an expression, the probability of h times by the log of p of h, summed over all the h's. So if I differentiate with respect to a single particular component, h, only the hth term in the summation is actually going to be a function of p of h. All the other ones will be constants. So that means this summation will disappear, and we just take the derivative then of this with respect to h, p of h. Is that clear? I see at least a few nodding heads. So just to say, we take the sum outside, we just need the h, the one here. The derivative of this with respect to p of h, well, that's a constant. That's not a function of p of h. So we get p old of h given by n. Times the derivative of this with respect to p of h. Well, the derivative of that is 1 over p of h. Okay. And this term here, well, this is clearly a constant, so that's 0. And this is going to apply a similar argument now. This term here is going to, it's only the h to 1, which is a function of p of h, and that's then just going to differentiate to 1, so we're going to get minus 9. Then we equate this to 0 to find the station. Okay, so now we can, this is sum over n, h. Okay, so we can bring this out. So 1 over ph, sum over n, p old of h given by n. So this says that pH is equal to 1 over lambda, sum over n, old of h given by n. Okay, so what the heck is this lambda? So this is something we need to figure out. Well, don't forget that we've got these constraints back here. The sum over pH is going to be 1, and so that's the probability distribution. So what that means is this lambda is just a constant, it's not a function of anything, right? So what that means is that because of that, it's just a proportionality term which we can figure out just by the requirement that pH itself has to be normalized. So what that means is that lambda is surely just the sum of the numerator over the state h. Right? So that means immediately we know that pH actually is equal to sum over h, p old h can be n.
Sum over n.
Sorry, sum over n, yeah. Sum over n, sum over h, p old h can be n. My n's and my h's look far too similarly. Now, this term here is 1. This p old is a distribution. So in fact that means that just capital N times. Okay, so this is going to be 1 over n. Sum over n. P So that's good, right? So now we've managed to get an expression for the new parameters as a function of the old parameters, the old distribution. And that's exactly what we want. So that's the kind of the Lagrangian constraint optimization approach, which is fine. You can do that. So that's good. So we've now maximized this expression with respect to this term. We've got to do this one still as well, right? So this is a little bit similar, but it's a slightly more painful, but not much. Let's just do it for completeness. So you should know pretty much exactly how this is going to go now. We're going to do the same. We do exactly the same thing, right? So we're going to say, well, where does p of vi? So let's choose a particular one. So p of vi given h. And where does that term occur? This is a little bit of a an awkward thing. It's really notationally problematic rather than conceptually problematic, I think. But let's just look at the wherever this thing is. I mean, it's certainly only going to occur in this term. Here. So we need to maximize this expression with respect to these kinds of things. Now, maybe it makes it a little bit easier to think about this, that v in this case is a binary variable, 0, 1. So we're going to parameterize this by, say, some theta I h. So this is the probability that the ith product is purchased with this h customer group is equal to theta IH. Okay, and I'm going to have then, of course, I need some constraints. What, do I need any constraints? I don't need any constraints. This is just a binary. The only thing I need is that theta IH is between 0 and 1. And that's it. Because there's a probability. So I want to write this thing now as a function of theta IH, and then try and optimize it. Okay. So the question is, what is the contribution of theta IH to this expression? So one way to think about that is to say, well, look, this sum over n is never going to cause a problem. Just put that there. Well, now I've got sum over I. So theta IH is only going to occur when, for the ith term in the summation. When this term is not I, this term here will never contain theta IH. It will be theta JH, where J is not equal to I. So it will be some additional term which is independent of theta IH, and I can ignore that because I'm only interested in the contributions to this from theta IH. So what's going to happen? Well, when the nth observation for I is in state 1, the probability of this is theta IH by definition. So that means I'm going to get a term log theta IH when VIN is equal to 1 only. Okay, so I can multiply by that indicator and say, well, when VIN is in state 1, I'll get that expression. Otherwise, I'll not get that expression. Okay, 0 there. When this is in state 0, I'll get 1 minus theta. This is the probability of generating 0, which is 1 minus the probability of generating 1. So I'm going to get plus log 1 minus theta h. When VIN is in state 0. Okay. And I have to multiply this whole thing by this term here, which is h is in state I. Sorry. So here, yeah. So and plus 2 constant terms, which I don't care about. Yeah, so just reiterating, this is the contribution of theta IH to the energy. The rest is constant. And now you need to maximize this with respect to theta IH. So this is a little bit easier because this, we don't have a Lagrangian problem here. So what do? Differentiate. Okay, so what's the derivative of this with respect to theta IH?
1 theta.
Yeah, 1 over theta IH. So this is a constant, so indicator BIN is this in state 1. We've got to differentiate this now with respect to theta IH. What is that?
Minus 1 over 1 minus theta IH.
Yes, minus 1 over theta IH. That's the indicator BIN is equal to 0. Provided I haven't screwed this whole thing up, get this all multiplied by P all of H B. So now that's good, right? So now we just need to solve this for theta IH. This is just an algebraic thing. So now this is a sum over n, so that's good. So this is just constant. So sum over n of this, what does that mean? That's just the number of times that variable I is in state, sitting in your data set. So we've got a sum over n of the number of times the variable I is in state 1. We've got a 1 over theta IH. Times by P of old H given Vn. Okay. Then we've got, we can put this on the right hand side, equals 1 over 1 minus theta IH, sum n of 0 pH given. That's good. So now we can, multiply this whole thing by theta times by 1 minus theta. So naturally we'll do. Let me call this term A, and this term B. So forward, down. So we're going to have 1 minus theta IH times by A is equal to theta times by A. Alright, so everybody happy? I'm a little bit tired today, so if I do make a mistake, then it wouldn't surprise me. So do shout out if you see anything important. So theta IH on the right hand side, B plus A is equal to A. So theta IH is equal to A plus B, where A and B are given by those times of that. So that's good. So we've now got again an expression for the new parameters as a function explicitly of the data and the old distribution. And that's exactly what we want. So the only thing we need to figure out then is, what is this P old of the latent variable? So that's the only thing that's sort of cropping up now in these expressions. Well, that's easy because that's just coming from base rule. So P H given B n is just proportional to P of Vn given H given the distribution from base rule, which is itself given by product over the indices of quantity Vn for this Bernoulli distribution I H. So that's fine. So all that means is you take each of your states of H and you evaluate this expression, and then you just normalize that to get a distribution for each index n in your data, and that gives you then your collection of these distributions. And you use those then whenever you've got these formula here you use those to evaluate those formula. That gives you then your updating mechanism. Okay. So let's see how that.
So those are the responsibilities. They're also known as, and so basically,
yeah,
the chance for any given data being produced by each of the clusters.
Yeah.
Essentially.
Yeah, that's right. I never remember exactly what they call these things. But responsibilities is one term which is banded around. So this is written, same thing written down. Okay, so we had this sort of recognition that actually, despite all this apparent complexity, in some sense the answer ought to be kind of obvious. In the sense that really, if you knew you didn't have any hidden variables or anything missing, in this case h is missing, right? You would just do maximum likelihood. The maximum likelihood just corresponds to counting. So the expression is that what you want to end up with is in these update formulae is essentially the maximum likelihood expression for the complete data case. Wherever you've got something which you didn't actually observe, you just take an expectation of that with respect to your old distribution. So your sort of indicator, which you'd have from the complete data case, is replaced by 1, 0, which is and that's like a deterministic distribution, right? But it's just replaced by the probability of getting such a data point, so like under this old distribution. Okay, so what you just to say here, this is like, well, what would you do if h were actually observed? This distribution P of V given h is where you just count how many times you saw V in state 1 and h in state J, and you just normalize it against that, right? So it would just be proportional to the number of times you see I in state 1 and h in state J, and indicated here. And all that you're doing is just replacing that indicator by your old distribution for generating such a data point. The denominator is just a normalization term. And the same for this. If you what's the probability of h is in state J? If you observed h, you just say, well, it's proportional to the number of times I see h in state J. That will be your indicator, the numerator, but actually you just replace that with this EM distribution. And then the denominator just normalizes that, ensures a distribution. So that's why, like I said last time, when you get a little bit more familiar with this, actually, you don't really need to write all this down. You can just jump directly to these end results. There's nothing to do. It's just a kind of, just will collapse. And if it doesn't give you this, then you made a mistake. Okay, so that's a kind of nice thing. So let's see this in action, if we can. Okay, so what's happening here is that we've got some 150 data points. This is the training data. So in this case, there are actually only 5 products. There are 150 customers. And I forgot which way around it is, but let's say black is 0 and white is 1. Okay, so in other words, this customer 1 bought product 5, not 4, they bought product 3, etc. Okay. The grey ones actually are missing data in this case. Not only is the H missing for that customer, but also some of the products. You don't know if this person, say, bought or didn't buy that product. It could also happen. And then we want to basically try to understand what kind of customer groups we have on this. So we run the EM, you saw that going along, that gave us this at every step. This is the log likelihood increasing. If this log likelihood is not increasing at every step, you've got a bug. either a conceptual bug in your algorithm development or an implementational bug. Very rarely you could have some kind of numerical bug. You could sort of run out of, precision in the computer to represent things properly, so you may have to somehow address that. But if it's not going up, there's something horribly wrong happening. Okay, so that's really good to check. And what we've done is then I actually generated this data, this 100 data points from a model of this form. So actually, this is another good thing you can do to check your algorithms. You could say, well, if I'm going to fit a model of this particular form, in this case a mixture of independent Bernoullis, what I could do is I could generate data from that model, some fake data, and then just see whether or not the algorithm is able to relearn the kind of correct parameters that I used to generate that data. So actually, in this case, probability, I have two mixing components, 1 and 2, and the probability of generating data from cluster number 1 was 0.3, for cluster number 2 was 0.7. So from these 100 data points, I just got that. I tried to re-estimate what is pH, and I got out that it's remarkably close to 0.3, suspiciously similar. I was very lucky there. And similarly for P of V given H, this is the true generating mechanism, the true parameters of it. And this is the one that I estimated from the data. So the one for each of the 5 products, we've got a sort of probability of the 2 groups of generating a 1, basically. So this is the probability of for cluster number 1 of generating a 1 for the first product was that. And this is what we estimated it to be. So these are quite similar. So the other thing to bear in mind is that what's going to happen typically is that you may have this sort of, if you play this game to see whether or not your algorithm is working, you may indeed say, well, this is what I had to start with, this is my parameters, and oh crikey, this one, number 1 was 0.7, number 2 was 0.3. Something's horribly going bad, I can't get it right. But bear in mind, there's this permutation symmetry again. It doesn't matter if you call this actually number 1 or number 2, it's irrelevant. So when you do the parameter checking, you need to just maybe commute the variables to make sure that you actually got the most sort of matching permutation. So a slightly more visually interesting demonstration. So yeah, people use this kind of stuff, by the way, really in practice, to cluster customers. So it's kind of interesting. It's not totally useless. You could do it perhaps say to cluster digit data. This is another kind of example where, in this case, this thing here is one of our data points. The data point is a binary vector, which is whatever it is. It's something like a 20 or 20 by 20 image. Okay? So there are something like, say, I don't remember the exact details, but there could be 400 pixels in this image, which are just going to stack into a vector. So that would be so D in this case would be 400, and we're going to have 5,000 digits, handwritten digits in our data set. And then I'm going to try to fit a mixture model of this Bernoulli form, independent Bernoullis, with 10 clusters. Okay, and this training data, because the algorithm doesn't know it, but actually there are 0 through to 9 handwritten digits in this thing. So it would be nice to think that actually sorry, I'm going to use 20 mixture. So it would be nice to think that the algorithm will say, oh, here, this is a cluster for the zeros, this is a cluster for the ones, 2s up to 9. So if we are lucky, that will happen. It may not happen. So we can run that, and it's a little bit slow, I'm afraid, on this little laptop. This exactly the same algorithm. There's no change. Except it's struggling a little bit. So this is our subset of the data. Probably fall asleep by the time this is finished. But anyway, we'll just cut it out when it's done one iteration, just to convince you that again, if you don't see this thing going up, you've got a problem. Okay, but I think that's enough. Okay, so we jump to the result, right? So the result is like this. These are actually the 20 clusters that were identified. And what do I mean by this as a cluster? Well, what I'm plotting here is a probability of generating a 1 for each pixel, right? So this means that this is very high, where it's red. It's very close to 1, probability of generating a 1 there. Okay. And as you'd expect, the probability of generating 1 for that cluster, say in the corner of this image, is very low. So these are the clusters it found, and they look a little bit like digits, which is nice. There's clearly 9, 0, 7, that's a 0, 7, 6, 1, 3, 2, probably a 7, but it's a little bit confused. It could be a 9. This one is a 4, another 4. This is probably a 3, though it's a little bit close to an 8 as well. This one is, I don't quite know what that is actually. This is a bit of a 5 kind of thing. Right? So now it's not perfect, right? I mean, you have to again remember that there are an awful lot of parameters here. This likelihood surface that we're trying to maximize. Yes.
Yeah. So I was going to say, the number of hidden layers that's chosen by yourself. Is that correct?
No, I just fixed it to 20.
Okay, I was going to say, why not choose 10? You know,
Okay, let's do it 10. I'm going to do 10 in this direction. So let's see if we can make it a bit faster by reducing the number of data points. Okay, let's run it and see what happens. I think what's likely to happen is that we will not get 10 digit cluster, because if you look at this one here, if there are 20, I think in this data set, I don't remember exactly, but I think there are roughly the same number of zeros and the same number of ones, etc. So you would like to think that it would, you would find, if you did 10 clusters, a 0, a 1 through to 9. So if you did 20, you might have been able to find 2 zeros, 2 ones, etc. But if we look at that, I think we can see how many 6s are there? 2. Okay.
There's 3 7s.
There's 3 7s.
There's
Yeah.
1 5.
There's 2 1s. 4s. So there's 2 4s. Yeah.
1 8.
There's only 1 8. Yeah.
Then it gets messy.
There's only really 1 9 as well, I think. So I think it's not, I think I just did that because, yeah, you don't get what you'd kind of hope them to get somehow. So the other thing to say is that this is really, these kind of problems, fitting these mixture modes is computationally, is numerically very difficult. This objective function it's riddled with local optima. Why is it riddled with local optima? Well, it's just a difficult problem. It's by construction got permutation symmetries. So that means for every sort of mode or little maximum in this likelihood function, there'll be an equivalent one somewhere else corresponding to permutation symmetry parameters. So that can cause some confusion for optimization algorithms because they don't know which symmetry, which property to use. Should I call myself cluster 1 or should I call myself cluster 2? They kind of jump around, jostling with each other, trying to decide what the permutation should actually be for that particular thing. So that can be problematic. And even with if you factor out that permutation symmetry, there are a lot of some solutions are better than others in the sense that there are just also many local optima. So what you really need to do, unfortunately, is to run these kind of routines very many times, see which, with different initializations, and see which one actually gives you the highest likelihood, log likelihood, and then you take that one as your best guess. See how it's going on. I should buy a better laptop, I think, for Christmas. Oh, there we go. Okay, so there are 10 digits here, and I think there are a reduced number of data points. I think there are only 500. Otherwise, it would take too long. Do we see that?
You got 2 zeros in it.
There are 2 zeros. Yeah. So there's no 4. There's a 4. There is.
4 and 9 are really similar, aren't they?
Yeah. There's no kind of obvious 7. I think. Right? So yeah, it's not great. So that's kind of, but it's not bad, right? So this kind of, what does it enable you to do? Well, you could do all kinds of things with it. So you could say, well, of course, visually to us it means something, but you have to imagine these may not be objects which are kind of visualizable in general. So that's kind of nice. You get this clustering effect. You could also use it to maybe do some kind of sort of pixel completion. So let's imagine somebody gave you an image, but some of the pixels were missing in the image. Right? What could you do? You could use this to clean up or to fill in the missing pixels in the image. How would you do that?
So we give them a single image.
Yeah, so let's imagine somebody gives you a new image with, say, and say the bottom half is it's all missing. So we would like maybe to complete this image in some sense, okay, it's a bit ambiguous here. It could be a 2. It might be a 3, but it could be it's certainly unlikely to be an 8, for example, 4. So we'd like to maybe draw a sample from a completed image. So what could we do? Well, we could use what is the model? The model looks like this. So in this case, H is an index from 1 to 10 and 1 to 20. And we've got a pixel from B1 through to B, say, 200, if it's a 20 by 20 image. So this one we will observe, but maybe these ones here, we don't know what they are. Let's say they are missing. So this is, say, fixed and observed. So what we could do is, given these fixed ones here, we can infer what is the distribution over pH given these observed variables. And then this, we can, given pH, we can sample states for the missing observations. So in other words, what is, you know, P is, let's call them, see, V101 to 200, given V1 to 100. Well, that's the sum over H of V101 to 200, given H and V1 to 100. So let's just do that way to start with. That's just a general expression. So this is H V 101 to 200, given H and V1 to 100, as P of H given V1 to 100. And this is, well, from here, given these things, given H by, because it's independent, so this is conditionally independent of, so this is conditionally independent of that, given H. So this is just the product over the individual indices of P, each V, VI, given H. So that says, okay, you just, given V1 to 100, you identify what H is. How do you do that? Well, that's just coming from Bayes' rule. So you would just say, this thing here is proportional to VV1 to 100, given H, times my P of H, which itself is a product of I from 1 to 100, PVI given H, multiplied by PH. So for each of your, in this case, say 20 images, you compute for your observed pixels this probability. Okay, this gives you then, you normalize it after that to get then a distribution over what are the likely H's corresponding to those observed ones. Then if you wanted to generate a sample to complete your image, you could say, well, to sample from this, I could sample first of all H from that distribution. And then given that H, I just generate, for my each pixel independently, I generate a state, 1 or 0, according to this probability, which you've learned from the training set. Okay, that would then, that would complete for you a something there. If we're slightly more alert, we could actually do a live demo of that, but maybe it's a bit too risky. You get the idea. So there's kind of, there are fun things you can do there. So you could, yeah. Okay, so let's go back to. Yeah, so the clustering questionnaires is another kind of thing you can do. You could say psychologists use these kind of things where you ask people questions. What kind of psychology? Yeah, I can't even think of what kind of things they like to ask people. But there are these kind of the books, right? There are 7 personality types apparently. I don't know, according to some psychologists. You know what I mean?
Plus or minus 2.
Plus or minus 2. I forgot what they're called. Yeah. I had a girlfriend who was very interested in this stuff at some point, but I forgot. I forgot how many there's supposed to be. Anyway, but anyway, the point is that they got to that number by having a questionnaire which was sent out to people, and I don't know what kind of questions they had, but things like you'd be put in various scenarios, and then you had to answer. What would you do? Would you get frustrated, angry, or whatever it would be? So then according to the responses, sometimes people wouldn't answer, so you didn't know what the response would be. But then they can just take these thousands of building questionnaires and try to figure out what kinds of are the typical groupings of people. So maybe some people are you know, they are risk takers, some people need comfort, so I don't know, whatever it is, right? And then they write books about this. And, so this is an example where you could use such a clustering mechanism. So the only thing that's is on here that we haven't discussed so far is that in that EM algorithm, we assume that all of the data was observed, the visible data was the V's were observed, okay? But actually, it's really trivial to extend it to the case where there's missing data in the questionnaire as well, or in the products. Because the only thing that's happening is that what's going to happen here in this term is that you're only going to be looking at the likelihood of the observed data. Okay. So probably the V, so if there's a missing VI, all it means is that that term is just not going to appear in this expression. It's just going to be absent. So it's very, very simple. When you just follow this through, I mean, you could just put an indicator there if you want, which would just say, you know, is the ith term present for the nth data point? It could be those indicator 1 or 0, and just carry through the remainder of the calculation. And these terms here, the probability of H given V, if it's missing, is fine. All it means is that because of this thing here, if you don't observe this data point, what's the probability of H? Well, it just means that you have to sum over this observation. And summing over this observation just means this vanishes to 1. Just becomes vacuous. So probability, you know what I mean?
Yeah.
So it's very, very simple. So you just carry through the calculation as before. So that's nice. So you can do questionnaire analyses with this. So the most celebrated example of a mixture model, discrete mixture model, is the Gaussian mixture model. And you will for sure come across this at some point in the other courses, in the other modules. I don't know if I want to go through the algebra with you. Did you do this in the other modules so far? You did. Did you go through the algebra with this?
Done it in machine vision.
You did the machine
Yeah,
vision.
we've been in it quite some detail. Yeah.
Okay, so anyway, so you know about this thing. It's a similar kind of setup to use the EM algorithm, and you know, you write down the energy. You have to maximize. It's a little bit more complicated in this case. You have to know something about how to do Lagrangians on matrices and vectors here. It's kind of fairly straightforward. And you get these updating rules, and you know, you get this kind of symmetry breaking property, which I think we saw at the demo last time. There's one thing I want to say about the EM actually here, particularly with this Gaussian case, and I don't know if it's something you've covered in your other module, but actually it's kind of weird, this EM algorithm, in the sense that if you said I want to maximize the likelihood for a Gaussian mixture model, so let's say you have some data points here, some data points here, and you're going to say fit 2 Gaussians for this data. If I put a Gaussian, say, centered on one of the data points here, and I make the width of this Gaussian very, very small, becomes infinitely limitingly small, what's going to happen is the likelihood of this data set is actually going to blow up to infinity. So how do we see that? Well, let's say that this is the probability of generating a data point x given the mean and the covariance for the ith cluster. Okay, so this is going to be so in general you have an xn minus m times by inverse covariance xn minus m. But if we set one of the means to be equal to one of the data points, okay, so this would then be 0 here. So get e to the 0, so we would just be left with one of the denominator terms. But what that means, if you set this covariance matrix to have essentially 0 determined to be of 0 width, this will actually go to 1 over 0 and explode. So in some sense, the question of what's the best mixture of Gaussians which will maximize the likelihood of a Gaussian mixture model is actually a silly question. Well, it's not a silly question, but the answer is it's unfortunate. Is you can do it just by simply putting a Gaussian on the data point, sending a data point, and making all of the covariances go to 0 with. That will blow up the likelihood of an infinite likelihood, and you can't beat that, right? That's the maximum likelihood solution. So what that means is that if you run this EM algorithm and you don't actually force any kind of constraint, you just run it, you know, as it's going along, and it converges, actually you get the non-maximum likelihood solution. You just get trapped in some local optimum. And that local optimum, you know, may be fortunate in the sense that it's kind of giving you a reasonable solution. But you're kind of, you know, it's not actually the maximum likelihood solution. You just, it's kind of bad form, right? To sort of think, well, you know, I got a reasonable answer just by look of the numerics of the algorithm, but it didn't give me actually the maximum likelihood. I mean, it's not. This is not really kind of satisfactory somehow. So, you know, there are various ways to address this. One thing is to include additional explicit constraints which can prevent these covariance matrices collapsing to 0. So you could say, for example, when I'm running the EM algorithm, when I update the covariance matrix, if that results in an update for which, say, one of the eigenvalues becomes too small or the determinant goes below a sort of specified threshold, then you stop updating the covariance matrix. You don't want it to shrink any further. More sophisticated things to do are to use a Bayesian version where you put a prior now over the means and covariance matrices. So in a sense, you could view actually the failure of maximum likelihood in this case really as a, what you're saying is, you know, any covariance matrix is fine with me. But actually, you don't really mean that. You know, you don't want covariance matrices with 0 width. That's a poor, that doesn't correspond to any kind of clustering, really. It's a kind of silly thing. So really what you mean is, you want a prior which says, I want a prior with sensible, to specify sensible covariance matrices, which would actually then be priors for the non-zero width covariance matrices. And you know, there are the typical things there are the Wishart distributions, etc., the generalizations of the inverse gamma distributions to the multivariate case. Okay. But there's, I mean, there's nothing really, you know, difficult about that. There's just some slight, you know, technical issues to address. Okay, so we saw this as well. That when you go through the iterations, as you go through the maximum likelihood EM step, there's jostling behavior as they're trying to break the symmetry that we have for the parameterization. We saw this last time, didn't we? Maybe. You don't see it super well. So this is actually kind of fairly classical behavior of EM, but in the beginning, you know, there's a bit of a jostling around where the parameters try to decide what am I going to, you know, call myself? Am I going to be responsible for this part of data or that part of data? You know, they need to kind of come to some agreement about breaking the symmetry. Then there's usually a fairly rapid sort of specialization into the clusters, and then it's a fairly slow convergence point. So EM is characteristically rather slow to converge, unfortunately. It's one of the things that people don't like about it. And again, you've got the log likelihood increasing. Cool.
Yes.
Okay. Just a couple of other things to say. So the Parson estimator is also a kind of mixture model. So what this does, it just basically it puts a bump of mass at some point. So it's very, very simple. It just says, well, you know, I've got this collection of data points, xn, and So it could be a Gaussian, for example. It places a Gaussian weight with mean at each, centered at each data point, with just to say a uniform probability. So in other words, it's a kind of it's kind of the world's simplest density estimator, density model. So it simply says, if you've got a collection of data points here, whatever they are, I'll use Gaussians for simplicity because it's more general than that. I want to make a probability distribution for these data points. So one thing you could do is to say, well, actually, what the Poisson estimator does, it simply says, well, it's going to be a mixture where I'm going to put a distribution centered on each of the training data points. And that's going to be some typically non-zero width distribution. In other words, it's some non-degenerate distribution. So it could be a Gaussian, for example, or something which is going to have some appreciable mass. And so that's the mixture model, but it's kind of, it's not totally pointless, but it's almost, for our purposes, totally pointless, because it doesn't have any, yes, it's true that you could generate data from this thing, you know, but it's kind of almost the same as empirical distribution. It doesn't really express any kind of lower dimensional parameterization of the data, right? It's just, you know, the whole point in some sense of making a model is you want to reduce this complex data set that you have and kind of compress it into some smaller, simpler description, right, which is kind of capturing the characteristics of the way the data is generated. Here, it's kind of poor. I mean, you know, basically I'm just, there's no clustering involved. I can't tell you really, you know, I'm not sort of really representing the data in a smaller number of clusters or some lower dimensional way. It's kind of a little bit pointless in some sense. The only thing you can really do with it is maybe, you know, maybe you could come along with some new data point and sort of say, well, you know, which is the most likely data point to sort of, you know, training data to kind of have been generated by, to have generated this particular new instance. It's not a very interesting model. K-means, which you must have done, I think, already, right? Which course did you do that in? You did that in
Methods, research methods.
research methods with Mark.
Mm.
So K-means is an extremely important algorithm for all kinds of things, and I just want to sort of tell you that it's related strongly to Gaussian mixture models and indeed the EM algorithm itself. Okay, so if we run the EM algorithm with Gaussian mixture models, we make some particular constraints. We say that each covariance matrix they're all the same. Okay, so all of the covariance matrices are sigma squared times by the density matrix. Okay, so normally in this Gaussian mixture model stuff, you know, you can have a different covariance matrix for each cluster. But if we constrain them all to be the same, they're all equal to sigma squared times by the density, so they're all totally isotropic, all the same. We're just going to be placing, so these are all supposed to be the same sort of spherical covariance matrix. The only thing that we're going to do is then decide where to place these means and what is the width of this thing. Okay, so that means that my mixture model is going to be the form generated data point X, the sum of in this case K mixtures, PI is my weighting mixture component, probabilities, and these are my Gaussian simpleton mean I, all with the same components. Now, in this case, what you can do is you can write down the EM algorithm, okay, which you've already derived in other places, and I don't really want to go through the details here. This is not examinable, by the way. This the derivation of the Gaussian mixture model for I'm just telling you this interest. There's stuff that we don't read it is, but the mixture of Gaussian is not. Then we can write down the updates of the EM algorithm, which I can go through, but if you look at the updates, you know, for the new covariance matrix, it's something like this. If you look at the updates for the new means, it's some kind of expectation of the data with respect to some responsibility, distribution, etc. And what we could do though is that we could now take the limit of this algorithm as these covariance matrices go towards 0. Okay? And actually, this does give something sensible in this case. Okay? And in the sense that the limit of the algorithm is meaningful. It's not a kind of pathological situation. So what will happen is that all of these kind of soft assignments, this averaging, actually gets replaced by a kind of thresholding procedure, where data points get hard assigned, there's hard assignment of data points to clusters. That's what happens when you take the limit of the EM algorithm as these covariance matrices shrink towards 0. And actually what will happen is that all these expectations that you're taking of the EM algorithm, they become simply that if mi is the closest data point to, closer to data point xn, these probabilities become 1. Otherwise they become 0. So you just essentially, when you do that, you get this algorithm, which is the celebrated k-means algorithm. So what it means is that you simply randomly assign these centers anywhere that you like, and then you simply say, well, for each data point, I find the closest center. So maybe I've got a data point here. In this case, this would be the closest center. I've got another data point here. It's also the closest center. So there are kind of assignments of data points to clusters. Okay. Once I've done that, essentially, I take the mean of the data points which are assigned to the centers. Okay. So in that case, those are the data points. These are the data points that get assigned to this center, etc. And then I just take those for each of those centers. It gives me a new mean, and I call that the new center. So that's actually the M step of the EM algorithm. So each new cluster mean is just the mean of the data points which are assigned to that cluster. And you just keep iterating this process of convergence. So this is kind of, I mean, it's kind of interesting that you can then recognize the classical k-means algorithm as actually a special case, a limiting case of the summation of EM. That's it's kind of nice. And you get this kind of effect here, some data points, and we basically then just end up finding these 3 cluster means. Again, this it sounds great and it's very nice, but it suffers from all the problems, or many of the problems that the Gaussian mixture model will also suffer from. Namely, if you don't initialize this well, then you could end up with a very unsatisfactory solution. So if I had, say, my data was like this, let's say I tried, I have to initialize some means with this k-means algorithm. Let's say I chose a mean here and I chose another mean there. That means that these data points here will always get assigned to this one and this one, which is good example.
If they were vertically above each other, would they, or?
It depends on the distribution in the other case, doesn't it?
Yeah.
2 centers in one cluster, they connected to and ignoring the other.
Sorry, say that again.
If you had 2 centers in one cluster which found 2 clusters in the single cluster and ignored the other one completely because it was closer.
Okay. Yeah. So do you mean?
Not if there were 2 subclusters as well.
So say again, you have 2
2 subclusters
Two
that were
subclusters,
close to
yeah.
each other, and then the means would just find those two clusters, subclusters, as two subclusters.
The problem is at this point here, this data point here is still going to get assigned.
If you
One of
if you
these
have
two.
Yeah.
if you have three centres, you could have two of the centres in the cluster on the right, and then one of them on the left. And what will happen is the one on the left will come between those two clusters and treat them as one cluster, and then you'll split the one on the right into two clusters.
Yeah, that could happen. Yeah, I agree. Yeah. So you may then not recognise the sort of subclusters here. Fortunately, that's true. That could happen. Anyway, so there are complex effects which could happen. But certainly, the ideal initialization would be somehow, that you could get unsatisfactory results, unfortunately. So what people do, there's a whole branch of kind of, heuristics really of how to initialize centers for k-means, and similarly how to initialize the means for the Gaussian mixture model. And it's all kind of, it's a little bit tricky stuff. Then the final thing to say about this is that in practice, what you typically do is when you do the Gaussian mixture model, is you initialize your covariance matrices to be very, very broad in the beginning, because if you initialize them to be extremely narrow, each Gaussian doesn't really feel the presence of the data points very far away from its mean, so it doesn't really get a kind of good understanding of the global structure of the data. So typically, you initialize your Gaussians at very, very wide covariance, so they can kind of then get a sense of where the data is. Okay, so that's all I want to say about discrete mixture models. Are there any questions before we break? So I'll tell you, by the way, in the last lecture, what's examinable and not examinable. Okay, so don't worry about that stuff. So let's come back at quarter to whatever it is, quarter to the hour.
I think David.